Yeah, it is 8:30. Guess I'll be using a whole lot less whiteboard this morning. I'm sorry.
Oh, it was like my calculus like more than half dropped out like halfway through the semester. I'll do like only a few people in the class.
Well, I don't think everybody's dropping out because I mean it's not like most everybody in the class is passing the class. I mean there's that if they're holding on to dreams of a 4.0 GPA, well, that may be a little bit out of reach for them, but it's not like half the students are about to fail with anything. But, well, I don't think they're dropping out. I think they just decided I don't know. Don't know why they didn't show up, but y'all did, so I'll teach y'all. Were all of you at the lab yesterday?
Yeah.
Okay, help me out. Who else was in the lab? Because, no, you know what? Never mind. I know who was in the lab. I do have that. It was the trig class before that. I don't know. Somebody absconded with the sign-in sheet, and I don't know who was there. All right. We are on chapter 4. We're talking about Newton's laws of motion. We talked about the first law of motion, the law of inertia. Or which one of you can recite it for me in the common parlance? When people talk about his first law of motion, what's the phrase they use to describe it?
Anything in motion will stay in motion. Set force, and anything at rest will stay at rest.
That's it in a nutshell. Hey, welcome. S'il vous plaît. A body at rest will stay at rest, and a body at motion will stay in motion, unless acted upon by an outside force. That is Newton's law of inertia. Of course, it was Galileo who actually introduced it. Newton got a lot of credit for a lot of stuff. And him being the president of the Royal Academy of Science at the time couldn't possibly have had anything to do with it. But what was Newton's great contribution? Because, like I pointed out, he didn't come up with the law of inertia. Galileo came up with that. It was Galileo who had the foresight to come to understand that the forces acting upon a body, the sum of these forces included friction, and that when you did a mental exercise or a mental thought experiment, as they call it, and you looked at how is motion affected as friction is removed, and he was able then to extrapolate the idea of a body in a frictionless environment and realize that it would just continue moving. Because up until Galileo, the idea was that there were two realms of motion: celestial motion, where the natural state of an object was to move in great circles. And then there was terrestrial motion, where the natural state of motion was for a body to be at rest, to be motionless. And it was Galileo who figured out that, no, that's not right. That the natural state of a body is to remain in whatever state it is as far as motion is concerned, is to be unaccelerated. That if it's at rest, it will stay at rest. If it's in motion, it will stay in motion until something else acts upon it. Galileo figured that out thousands of years before Newton was born. And all of the things Newton, all of his laws, these were not new ideas. These are not things that he just suddenly came up with out of thin air. These were thoughts and ideas. and understandings that people had held for years by the time he came around. But what he did, no one else before him was able to do, was he unified the two realms of celestial motion and terrestrial motion. And he demonstrated that the same laws govern motion in both realms. It's one universe. Both, whether you're in orbit, in space, or whether you're on the earth, the same laws of motion will govern your motion wherever you are in both realms. And he unified those two realms, so he developed a single universal theory of motion in these three laws. And he also invented calculus, wrote the Principia Mathematica. He did some other stuff too. Okay, I don't want to diminish his contribution to science, but when he came up with these three laws, he wasn't coming up with a new idea. He was unifying what we already understood. He was expanding our understanding so that what we already knew to be true suddenly made more sense. And we realized how it applied not just to our experience, but beyond our own experience and our own perception. That is where these laws of motion came in. That's why they became significant. I also mentioned that there's something called an inertial reference frame, because we've already seen relativity matters in physics and in the world around us. That anything you measure is going to be measured relative to some reference frame. Okay, so you can't get away from that. Newton's law of inertia, and in fact there's others as well, but for the moment, we're looking at the inertial law of inertia, his first law of motion. It is valid if and only if you're talking about it in reference to an inertial reference frame. Now, what does that mean? And one of you tell me what an inertial reference frame is. That makes sense. We're talking about inertia. So you would need an inertial frame of reference. But what does that mean? What constitutes an inertial reference frame? It's a frame of reference that is unaccelerated. And basically that is, hey, hello, bonjour, welcome, bienvenue. The law of inertia, basically, if you want to summarize it, boil it down to brass tacks, is simply a statement of the fact that the natural state of any body is to remain unaccelerated. Okay? So an inertial reference frame is a reference frame that is unaccelerated. So if you're flying in an airplane or riding on a train and you're zipping along at a couple 100 miles an hour relative to the ground, you can still set your cup of coffee on a little tray table right in front of you, and it'll sit there and it won't be any different than sitting it on the table right here. You can pick it up, you can take a sip out of it, no problem. As long as the train or the airplane or the car is unaccelerated. Will that cup of coffee, that once you set it down and it is in your inertial reference frame, it is at rest relative to you and relative to the frame of reference you're in, to the airplane or the car, it's at rest. If the car suddenly slams on its brakes or if the airplane suddenly takes a nosedive, is that cup of coffee going to stay at rest sitting there on the dashboard in front of you? It is not. It is going to accelerate suddenly and abruptly and quite messily and all over you. Okay? You've seen the videos on YouTube, I'm sure, of some idiot trying to drink a slushie on a roller coaster. Does not end well. Say again? They have actually, surely y'all have seen that video. I mean, they've made dozens of them. It's like every kid with a camera wanted to try and drink a slushie. Or there's one I remember where he was trying to drink it on the back of a motorcycle. Like, well, it works fine as long as until the driver of the motorcycle decides to pop a wheelie and suddenly that slushie don't act right no more. That's an inertial reference. All that means is it's a frame of reference that is unaccelerated. If it's moving, it stays moving at a constant speed in a straight line. Remembering that acceleration is any change in velocity, and since velocity is a vector with magnitude and direction, any change in magnitude or any change in direction is an acceleration. Now, that also brings up a question that is actually kind of philosophical. And that is, what is inertia? I mean, what is mass? Because they're kind of the same thing. Well, mass is the measure of matter. If you have matter, then that matter has some mass. And we've talked about this, so I know this is just kind of a recap of where we've already been, but that mass will be the same whether you're on Earth, on the moon, in orbit, in a spaceship. Doesn't matter. Weight and mass are not the same thing. Weight is the force that that matter exerts on whatever it's resting upon. Okay, the weight is a force measured in newtons or foot-pounds per second squared. No, actually, weight would be measured in pounds. Doesn't matter. A 1,000 kilogram block of iron is going to be 1,000 kilograms, whether it's sitting on the ground on Earth, or if it's in orbit around you. If it's in orbit, it's basically weightless. If it's on the Earth, it weighs a ton, literally. 1,000 kilograms is 1 metric ton, or 2,200 pounds. Here's the thing: that metric ton, that 1,000 kilogram block of iron, is going to resist any force to accelerate it equally on Earth and in orbit. So if you want to accelerate it while you're in orbit, it's still going to require force. This brings us to the second law of motion. Can anyone tell me what is the second law of motion? Force is mass times acceleration. The force that you apply, the sum of the forces acting on a body, on a quantity of matter, will accelerate proportionally to the mass, to the mass of that body. Again, force and acceleration are both vector quantities. Normally, now if you've got an object floating in space, then there's no forces acting upon it. Are there forces acting on this cup right now? What are they? What forces are acting on it? Gravity is one. And so we know that the acceleration due to gravity, acceleration due to gravity is the acceleration. Wrote that wrong. The mass of that coffee and cup are being accelerated by the force of gravity. The force they're experiencing is the force due to gravity. It's one of those phrases that colloquially people use it. You know what they mean. Technically, they're not actually correct. But we know what we're talking about when we talk about the force of gravity. We're talking about the force experienced by a mass due to the acceleration of gravity. But it's not moving. And if a force is acting on that mass, it should be moving. Right? Not if there's what? An equal force pushing back up against it. Exactly. This funny looking E character here, everybody recognize it? Uppercase Greek sigma. And it means the sum. It's a summation symbol. You probably encountered it in algebra. It's telling us that the vector sum of all of the forces acting upon that body will produce a net acceleration of that body. There's a name for that force. While it's sitting on that table and that table is not moving, it's called the normal force. The normal force is simply the equal and opposite. Okay, I would say it's the gravity, but it isn't always equal and opposite to gravity. It is whenever something is stationary. But it's going to be equal and opposite. It's going to be pushing in the opposite direction. And this is bringing us to the third of Newton's laws of motion. Now, can anyone tell me what people say? What's the common phrase you hear when people talk about the third law of motion? And I would say it ain't rocket science, except it kind of is. Every action, there's an equal and opposite reaction. Exactly. If this cup is exerting a force on this table is exerting an equal and opposite force against as long as it's stationary. Do they have a mathematical expression that they use in this book? No. Don't see. Yeah. We'll just leave it at that. Whatever force you apply to something, that something applies an equal force back against you. Now, we kind of touched on this before and a little bit in the lab yesterday. So let's think about this a little more in depth now. If I push on this chair, that means that that chair is going to push back against me with exactly the same amount of force that I apply to it. Okay? But only the chair moves. I don't. How can that be? If the chair was pushing back on me with the equal and opposite force that I was pushing on it with, how is it that the chair was accelerated, but I was not? Friction. Exactly. It's not the one force that causes the acceleration. It's the sum of the forces. Now, I did not push on this chair with as much force as I was capable of generating. Okay, I only pushed it enough to move. If I wanted to push it as hard as I could slide it all the way down to the end of the room and make it smash into that wall. I could accelerate it a lot more than just that little bit. So whatever that force was that I applied to it was that much. It was pushing back against me with the same amount of force. But what were the vector sum of the forces operating on me? There was me pushing on the chair, so there was the chair pushing back on me with the same force. Okay? But there's also me pushing on the floor, and the floor pushing back on me with the force of friction. Okay? So, how hard was I pushing on the floor with friction? What was the force of friction that I was pushing on the floor with? I'm pushing on the floor against the force of friction, which means the floor is pushing back against me with the same force. What was this force? How big? What was the magnitude of this force? The force between the floor pushing on me with friction. No, we don't. Okay, I understand where you're going. Let me put you back a little bit. Let's not worry about trying to plug in numbers and actually do the math. We're doing a thought experiment here, so let's just think about the physics of what's going on. We'll worry about trying to quantify it later. But for right now, let's just think about what we do know. We know that the chair is pushing on me with a force in that direction, equal and opposite to the force that I'm applying to the chair. But we also know that the floor, the friction between me and the floor, is pushing in exactly the opposite direction with exactly the same amount of magnitude. This force and that force are equal and opposite. Okay, so that's how we know how strong this force is, because we know how strong this force is. They're equal and opposite. And since the vector sum of the forces acting on my body as I push on that chair cancel out to zero, my net acceleration is zero. But at the same time, I'm pushing on the chair with the same amount of force chair's pushing back on that the chair's pushing back on me. But I'm pushing the chair with that much force. The force of friction between the floor and the chair is pushing back in the opposite direction. But the force of friction is proportional to the weight of the chair and gravity and the coefficient of friction. Just like the friction between me and the floor is proportional to the coefficient of friction, my weight, the force of gravity, how sticky or how rough my shoes are. The force of friction between me and the floor is at least strong enough to be equal and opposite to the force I'm pushing on the chair with. The force of friction between the floor and the chair is not. There's a limit to that static friction that's equal to the coefficient of friction and the weight of the chair pushing down on the floor. And once I push on it hard enough to exceed that maximum force due to friction, then suddenly there is a net force acting on the chair that is not zero, and the chair moves. Okay? Have I thoroughly confused you? Okay? I push against the chair, but I'm also pushing against the floor. The chair pushes back with an equal and opposite force. The floor pushes back with an equal and opposite force, as long as I don't exceed the force due to friction between me and the floor. What if I go push on that wall? Or this door, this wall? The force of friction between me and the floor is less than the force of that wall not wanting to move. Okay? So I was the one that got accelerated. I was the one that moved. The chair is much lighter. I can move the chair. Now, it's important to understand, though, that the net acceleration of this chair is not as great as it would have been if there were no friction. So the total force that I apply to this chair does not translate into accelerating the chair. Okay? In other words, if we knew a number, if we knew what that number was, how much force I was applying to that chair, and we calculated how fast that would accelerate the chair, we would find out that the chair didn't go anywhere near that fast, because there's also the force of friction opposing. And it's the sum of the vector sum of the forces, the net force, if you will, acting on the chair that produces the acceleration. Does that make sense? If you want to take this thought experiment to the next level, just imagine trying to push something if you're standing on ice. We've got a winter storm. I don't think it's going to get to us, but you've been around when there's been ice all over the ground on the sidewalks and everything. Could you push something when you can't hardly even walk when you're standing on ice? You can't even push yourself forward, because every time you try to push with your foot, it just slides backwards. Just your own inertia is enough to overcome the force of friction between your foot and the ice. And you don't want to move. Well, you do want to move, but you end up moving not at all like you intended. You end up falling on your face. Everybody getting this? Okay. They talk about here in example 4. about the forces that move a car. People think, well, it's the engine that moves the car. Well, it's the engine that produces the power. But all the engine does is turn the wheels. The wheels grip the ground, and as they rotate, they push the car forward. And if you've ever watched, what do they call that show, Street Outlaws, about drag racers in Oklahoma City? If you ever watch that, you know how important they take friction between tires and the pavement. This is the important part. When you think about whether or not something is going to move, when you push on it, you have to consider all of the forces acting. Force due to gravity, the normal force. Does everybody understand the normal force? Weight of this cup, pushing it down, it's not moving. That means there is a force. This table is exerting an equal and opposite force against it. This normal force thing is going to come up when we start looking at friction. I'm going to talk about putting a box on an inclined plane. Now, the gravity is acting on this box straight down. Okay. I don't know why I drew that line there. But that force of gravity then gets broken down into two components. There's this force that's pushing against the inclined plane, and then there is this component of the gravity force that's pushing it down along the inclined plane. So you've got to figure out what the angle is and decompose this force due to gravity into the two components. You've got this force, the normal force, that's preventing the box from moving this way. And then you've got this force that's accelerating the box down the incline. There's also a force due to friction pushing against the static coefficient of friction. And then after it starts moving, there'll be a kinetic coefficient of friction. But I'm not getting there yet. The point is, there's a coefficient of friction, so there's a friction force pushing this way. And when this vector, when this component of the gravity, the force due to gravity, exceeds the force of the friction, that's when the box will start to slide down the incline. In fact, probably, and I think there's one of our labs that we're going to do where you measure the coefficient of friction by putting your box on an incline, on a plane, on a track, and then slowly raising one end of it, increasing theta until the box breaks free and starts to slide, and then you've got your measured angle incline, and you can then use that to calculate the coefficient, the force due to friction, which you can then calculate the coefficient of friction. But that will come later. Here's a good example. And we got time, so I want to look at these. Before we start getting into such as all that. Shows here two people pulling a boat down a channel. You got one one bank here, one bank here. In between, you got water. And you got a boat. Now, tied to that boat are two ropes. One here and one here. And you got little guys pulling the boat. According to the book, they say this guy's got an angle of 37 degrees, this guy's got an angle of 45 degrees. And this guy is pulling with a force of 40 newtons. And this guy's pulling with a force of 30 newtons. So now they're asking, what is the net acceleration? What is the net force acting on this boat? Well, this one we can break down. This 40 Newton boat vector, we can break down into times the cosine of 45 degrees and 40 times the sine of 45 degrees, which the cosine and sine are both what? 1 over the square root of 2. So 40 divided by the square root of 2. Oh yeah, 28.3 newtons. This way, and 28.3 newtons this way. Or 40 newtons at 45 degrees equals 28.3 newtons I plus 28.3 newtons J, where plus Y is up. That leaves now, what is this one? This we've got 30 newtons at 37 degrees. Which gets broken into 30 times the cosine of 37 degrees and 30 times the sine of 37 degrees. Or 24.0 I n 18.1 J, except it's pointing down, so it's minus 18.1 J. That means we now have this 30 cosine, 30 Newton at 37 degrees is equal to 24.0 I, 24.0 newtons I, minus 18.1 newtons J. Now that we've converted the two vectors into rectangular coordinates, we can simply add the components to find out the net vector, the net force acting on this boat. we're assuming that there's basically zero resistance of it floating in the water. So that we're neglecting friction between the boat and the water. 28.3 newtons I plus 28.3 newtons J plus 24.0 newtons I minus 18.1 newtons J gives us a net force of 52.3 newtons I plus, I'm not doing that one in my head, 28.3 minus 18.1, 10.2 newtons J. That is the net vector, the net force accelerating this boat. So what does that tell you? Well, to make it more plain, let's convert this back into a polar form vector so we can kind of get a picture of it. We know that its magnitude is going to be the square root of 52.3 plus squared plus 10.2 squared, which will equal 53.3 newtons. And its angle will be 10.2 divided by 52.3 gives us that, take the inverse tangent, at 11.0 degrees. That's the net vector. The net force acting on this boat is pulling it this way. What does that tell you? This guy needs to back off a little bit because he's going to pull the boat into that bank before they get all the way down the stream. Hey, look at that. I got the same answer as the book. Who has any questions or thoughts? This is pretty profound stuff. I mean, this tells you that if there was no, we tend to think of friction as a bad thing. It's always draining energy. It makes us have to work harder. But it also tells us that if it wasn't for friction, we couldn't do anything. You really need friction to be able to do anything. You can't. Right? Just think about trying to get anywhere, trying to do anything out on an icy surface. Other than ice skating, you can't really do anything. And the only reason you can ice skate is because you create this very hard, very strong lateral friction between your blade and your skate. Anybody have any questions from the homework? Has anybody looked at the homework? reemphasize one thing, and that is, because I don't know that you're going to get this anywhere else. And there are a lot of people that impugn Isaac Newton because and would say, oh, he didn't really invent calculus. Leibniz invented calculus, and he only got credit because he was president of whatever, the Royal Academy of Sciences or something. And I'm not saying that that didn't have something to do with it, but the truth is, all the actual evidence suggests that, improbable as it may have been, Newton and Leibniz actually both invented calculus at the same time, independently of each other. Does holding a position of power like he did have perks? Yeah, you bet. It does now. It did then, and it always will. Look at just in very recent history. Look at Goddard, Samuel Pierpont Goddard. He was in with the Washington D.C. crowd back in the 19th century. They gave him huge grants, like $50,000, $60,000, $70,000 grants. One to develop an engine that was capable of producing enough thrust to weight, power to weight ratio enough to power a heavier than air aircraft that was capable of carrying a human being, carrying a man. And after he did the engine, then they gave him more money and said, now build the airplane. They ended up investing like $150,000 or something. This is $150,000 19th century dollars. Okay, so we're talking millions today. And after two failed attempts to launch this airplane that he was working on, he had nothing. That's it. Two failed attempts to launch his airplane. And a week after his second failed attempt, a couple of bicycle mechanic brothers from Ohio drove down to Kitty Hawk and launched the first airplane that they did, Orville and Wilbur Wright. And they did it with a complete total budget of $8,000, which was no small sum back then by any means, but it was nowhere near the $150,000 that Goddard had spent. Goddard or Lane? I may be confusing Goddard and Lane. But the point is, Orville and Wilbur Wright got credit for inventing the airplane because they did it first. But Langley or Goddard or whoever still got the space centers, Air Force bases named after them. Okay, so there are perks with having the position of power. But what Newton did was by no stretch of the imagination trivial. He unified these two, until then thought, completely separate realms of physics. As far as people could figure out, the physics on Earth were nothing like the physics in the heavens. They were two different worlds, two different realms. Newton figured out that no, everything that's true here applies there as well. Everything that is true there applies here as well. And he unified this, which, as you go through the history of science and advancement, it's those moments of unification that are always the sea change moments. Those are the seminal moments where our understanding grows with leaps and bounds. It's not sufficient to just have the knowledge. I wrote up here. Knowledge is only the beginning. It's just one step removed from ignorance. Until you actually understand what you know, you're just one notch above ignorance on the left. Newton gave us a whole new level of understanding. Later on, Maxwell Clark would do the same thing with electricity and magnetism. When he would develop his equations. Again, like Newton. He wasn't introducing anything new. Everything he described in those equations were things that were already known and established, independent. But he unified electricity and magnetism together to show that they were inexorably linked. And when he did, light fell out of the equation. An understanding of light and its role in the universe. The same thing with Einstein and his theory of relativity. You may have noticed we've been talking about relativity all the way back to Galileo. And even before then, with the philosophers, Aristotle and Socrates, and Ptolemy, relativity was not a new idea at all. It was well understood. You had to have frames of reference when you describe motion. But Einstein introduced this notion that what if, instead of looking at what changes when you change from one frame of reference to another, why don't we look at what doesn't change, what stays the same? Now, in his case, it was the speed of light. That was always going to be the same in every frame of reference. That's what he started working with. With Newton, what stays the same? Well, it's everything. All of the laws of motion stay the same, regardless of which realm you're in, as long as you're in an inertial reference. Even when Einstein introduced relativity, first he said, well, it's special relativity, and then he advanced that to his more general relativity. But this is the genius of what Galileo introduced, of what Newton introduced, Maxwell introduced. They didn't really come up with anything new. They just gave us an understanding of a greater understanding of what we already knew. And that's enough of that soapbox for today. Let's go back to our physics class. And yeah, we got a couple more minutes. So if does anyone have any questions, comments, thoughts? Everybody sign in? 5, 1, 2, 3, 4. Yep, everybody signed in. All right. See y'all Monday.